All right. Hello, everyone. Evgeny is here, and it's 8 p.m. GMT and very comfortable 10 p.m. here in Sweden. So I'm very happy to start 11th season of VSA Online. I'm very excited about the program that we prepared for you. So let me very quickly remind you the couple of things. So here is the address you can use to access our website. And here you see the current program. So, and I'm very happy to introduce the opening talk of the season. So, Graham Bent will um, open the VSA Online now. So, without any further delay, Graham, the floor is yours. So I stop sharing.
Okay, you should be able to see that, yeah?
Yeah, yes.
Okay, well, good evening, everyone, or good morning, or wherever you are. Um, yeah, this is a talk that I was supposed to give last year. Anyway, we're here tonight. I'm not going to sort of show you any new approaches to VSA. The purpose of this talk is really to explain to you some work that we did for one of our customers, who are the Defence Science and Technology Laboratory in the United Kingdom. This work is joint work with Cardiff University, with the University of Strathclyde in Glasgow, and also with a company called Fraser Nash, who run a government programme in the UK called Serapis. So my name's Graham Bent. I'm Neurosynapse Limited. I used to work for IBM Research for a long time, and then set up my own little company so I could work with other people other than IBM. So I'm just going to talk this evening about a demonstration of vector symbolic architecture, AI at the network edge. Our customers are really interested in how you do AI at the edge of a network when you just don't have the resources that you might have in a standard cloud or in a high bandwidth environment. And VSA fits neatly into the sort of thing that they want to do. So I'm going to take you through a bit of the background to the things that we were doing. And one of the reasons for this talk is, how do you explain VSA to a semi-technical audience, but an audience that doesn't really understand it? And you might find some of the slides quite useful to explain that to other people. And so the fundamental question is, what is human cognition? When we talk about artificial intelligence, we're really talking about some form of cognition, and there are lots of sort of definitions of cognition, but fundamentally, the components, if you like, of human cognition are perception, that is, allowing people to take in information through their senses, and then to utilize that information to interact with the world. There's this concept of attention, which allows us to focus on specific stimuli in the environment. There's the use of memory. How do we encode and store and retrieve information? And that's obviously critical for the learning process. And how do we retain knowledge and then recover knowledge from our memory? There are a whole area of things to do with learning. How do we take in new things? How can we synthesize information? How can we integrate it together? There's reasoning and planning, and that requires the capability to formulate and evaluate and select from a sequence of thoughts and actions to achieve a desired goal. And then usually in human cognition definitions, there's this whole area of language and communication. How do you interact with other things? So I'm going to take you through this in the context of our customer, who's a military customer. They advise the military, and the military often talk about a thing called the OODA loop, the observe, orient, decide, and act cycle. it's not just one cycle; it's multiple cycles, as you can see here in this slide. But basically, you've got observe, where you're observing the environment through sensors or whatever it is. You have to orient to the goal, what it is you're trying to achieve. You've got to make decisions and you've got to take actions. That's the standard John Boyd OODA loop cycle. But we can sort of map. Oops, sorry, I need to click on there. We can sort of map these cognitive processing functions onto the OODA loop cycle. It's a very similar sort of cycle of activities. So observe is perception and attention. To orientate, we're using memory, we're using learning. If we want to decide, it's a combination of memory, learning, reasoning, and planning. And then we've got to act. And the act often involves communicating either with actuators that we want to act, or communicating with other agents or humans. So that's the basic cycle. And what we wanted to do was to demonstrate that we could perform the whole of the OODA loop cycle just using vectors. That's really the idea. So can we in some way use VSA, the vector representations in VSA, to perform all of these different functions? Now, most of you, if not all of you, are familiar with Chris Elias Smith's book on how to build a brain, and where he introduces the idea of the semantic pointer architecture. But the really important thing about Chris's book is that he goes through all of these ideas of cognition and the way in which cognitive scientists and so on describe different functions. And in his book, he clearly tries to show that we can use symbolic vectors to perform most of these functions. And the key statement really from How to Build a Brain is that symbolic vectors are simultaneously a semantic description of a concept, and they're also a pointer to the concept. And when you get your head around that idea, then you really understand what VSA is all about. Now, I'm not going to bore you and with motherhood and apple pie and explain to you all the different ways. You're probably all aware of the different vector representations, from holographic reduced representations, binary spatter codes, and so on. But the various operations are relatively straightforward. There's just vector generation, there are vector binding operations, there are bundling operations, there are unbundling operations, and there's cleanup memory. But one of the things that we spent quite a bit of time looking at was the ability to create hierarchical representations of these vectors. So you can have vectors of vectors and different layers where you can build up higher and higher representations of the vectors. Now, when you're talking to a non-technical audience, trying to get the idea across of what this vector representation is all about is actually quite difficult. So we thought we'd try to get this across to our military customers by giving them a very simple idea about how these vectors work. And the idea that we came up with was, how do you make a smoothie? And of course, we know that what we want is a fruit of different kinds to put into our smoothie, but what we don't want is a fruit salad. We actually want a smoothie. What's that got to do with our vector symbolic architecture? Well, what we really want is a common representation of everything. So we'd like a common representation, some form of representing fruit in different ways. And one way to think about that is that you mash up your bananas into a banana hypervector. You've got a blueberry hypervector and a strawberry hypervector and a kiwi hypervector. And in a sense, what you've now got is a sort of distributed representative, is then make a smoothie. And again, what you don't want to do is to produce something like this layered smoothie here, because one of the concepts you want to get across is that the vector that we've got, this vector of vectors, when we combine these things together, is a distributed representation. And of course, that is exactly what we do when we're doing binding and bundling. We've got a common representation of anything that we want. We can represent anything as a hypervector, and we can combine them together to produce this smoothie. But the wonderful thing about the the hypervector representation, as Penty always pointed out, is that we can go from that distributed representation, and through an unbinding process, we can actually recover the different representations, the banana, hypervector, and so on, and we can then map back, because we bundle the idea of we bound the idea of banana to the banana hypervector, so we can recover the original vectors through a cleanup memory process. Now, of course, because it's a distributed representation, the other thing is that if we've only got part of the vector, or we reduce the size of the vector in some way, then we still get a fuzzy representation of the vector. And from that fuzzy representation, using a cleanup memory, we can recover the original thing. So we can represent anything in a hypervector representation. We can create a vector of vectors to represent or smoothie or fruit salad smoothie, and we can then recover the components of it. And that's the fundamental idea that we're trying to get across. So if we were to choose a particular way of representing the vectors, and in this particular case, we're using binary hypervectors, you can think of these hypervectors as, so that's essentially what we've got. If we've got hyperdimensional vectors, we've got a 10,000 dimensional vector. It's essentially each point in a 10,000 dimensional hypercube is one of those vectors. And so vectors that are similar are going to be in a similar location within the hypercube. And of course, we can then measure Hamming similarity to determine how similar vectors are. And the idea is that we can represent anything, maps or images or workflows or whatever we want, in a common representation. So that's the idea, that everything in our model is in a common representation. And so what we want in our neuroscience model is that we want something that is a key that can process for human cognition. But the idea behind using the hypervectors is that because we're using high dimensional vectors, we get all these nice properties that we can use. We can think of the vectors like a semantic QR code. If you think of the binary vector just presented as a sort of 1-0 code like this, you can think of the vector semantically representing something, and we can think of it as a semantic QR code. So we're trying to get these ideas across to the people we're talking to. And it's already been demonstrated in the literature, and that's what we've been doing in the VSA webinars over the years. It's an effective alternative in many cases to current mainstream AI techniques. I'll come back to why that is in a moment. But the nice thing about these vectors, and particularly for our military customers, is that we can have them as very compact representations. So although we might want to deal with 10 kilobit hypervectors for the high dimensionality, because it's a distributed representation, we can take sections of it, say as small as 1K binary digits, and we still can recover something. We still have a semantic representation of the thing that's represented even by a 10 kilobit vector. And the reason our customer was interested in this was that they're compatible with the idea that they have. They call it SWaP-C, but it's low size, weight, power, and cost. And also, as I used to work for IBM Research, they are compatible in lots of ways with the next generation of neuromorphic processors. So that there's lots going for this representation. But the question that our customer had was, well, how can VSA, or we talked about hyperdimensional computing as an analog of that, or is the same thing. How can we support cognitive capabilities that are required for the things the military want to do, particularly intelligence, surveillance, and reconnaissance, the thing they call ISR. So if you look at a typical ISR, they have to go through these things that we see in this OODA loop cycle. You have to observe the environment that you're operating in. And of course, there are all sorts of different ways of observing it. There's open source intelligence, there's human intelligence, there's signal intelligence, there's image intelligence. There are all sorts of different ways in which they want to gather the information. And what we were trying to get across to them was that in principle, we can represent pretty much anything as a hypervector. And so what we did initially for them was a literature review. And of course, in the literature reviews, we've seen over the many presentations we've had during the VSA webinar series, that every time we try to use VSA, we can show that whether we're doing semantic encoding of images, or we're doing semantic encoding of signals, or temporal signals, that in each case, VSA HDC processing is either as good as or better than state of the art. And I've just got a couple of examples here that we use to sort of demonstrate that. And we do actually use some of the things from these two papers in our demonstration that I'll get to in a little while. So from the observed perspective, it's that there are ways to represent images or time varying signals in a very efficient way as hypervectors. But of course, lots of people want to use different types of deep neural network to represent things, and so convolutional networks, or whatever we have, or different types of encoder networks. And of course, internal to all these networks, essentially what they're doing is generating vectors, and we can always map the vector representation that we have from any type of deep neural network. We can get at the vector representation at the appropriate level within the deep neural network and map that into our 10 kilobit or whatever VSA representation we want. And the nice thing about that is that a fusion process between, say, an unattended ground sensor, which you see at the bottom here, and a camera sensor, is that we can map the two things together, and just simply by superposition, we can get a fused hypervector that represents both the visual aspects and the acoustic aspects of a particular thing that we're observing. And of course, we can do that in a hierarchical way to get as complex representation as we like, a semantic vector, effectively, that represents all of the components of the system we're trying to describe. Now, when it comes to things like text representation, of course, we've got large language models, and with large language models, we can do exactly the same thing. We can take vector encodings from layers within the large language model, and we can map those vector representations into the same 10 kilobit or whatever representation we're choosing for our particular demonstration. And in our case, we've done that with various large language models. We've been able to extract vectors that can represent semantic concepts that we want to represent in our agent, as you'll see a little bit later. And again, we can take the vector representation from the large language model and map it into this common binary representation. So that's the observe. What about orient? What is this sense making and cognitive map or cognitive representation? And here what we've been looking at is, can we represent different types of information? We need to orientate to space and time. We need to orient to a mission that we're trying to perform. Can we represent these sorts of ideas in our hypervector representation? And of course, one potential way of doing that is to map things that we very often want to map things in the spatial domain into some sort of representation within our hypercube brain, if you want to call it that. Or we may want to represent knowledge graphs or whatever into the same representation. And some of you may remember we had a really good presentation from it was Christoph Stokel, I think, and colleagues at Graz University. That they introduced us a few sessions ago to the idea of cognitive map learners. And so I implemented their cognitive map learner in order to be able to just demonstrate how easy it was to start off with a sort of random representation of vectors. And if you've got a sort of real world grid of objects and you're trying to work out how you might navigate through this space, how you can, using their approach to cognitive map learners, you can, over time, with a number of random walks, just randomly walking around this maze, you can actually create a cognitive map representation where the colors here represent the Hamming distance from the point here, which is in yellow, to the edge of the network. That's just a measure of the Hamming distance. And of course, where you've got barriers, you can't go through the barriers, so those become essentially an infinite Hamming distance. So the question is, well, do we have to do it that way? Do we have to learn these representations? And one of the things that you soon quickly realize is that you can actually engineer these cognitive maps by using the circular hypervector representation or the linear or level hypervector representation, where in terms of the circular hypervector representation, if you have two vectors, the Hamming distance between them represents the angular distance between the two hypervectors. And in the case of the linear hypervectors, it's the linear distance between any two vectors that give you the distance between them. And of course, if you take the linear hypervectors and you want to create a cognitive map in 2 dimensions, all you need to do is bind the x vector, x linear hypervector, with the y linear hypervector, and you get something that looks very similar to the thing that we looked at before, that we learned here. You end up with pretty much the same sort of representation. So there's a quick way of actually generating these cognitive maps. And this is just an example of one such map. What I'm going to do is have an agent that's at the position here that you see in yellow. And what you can do is you don't have to just have one spatial map. You can tile them together. In here we're just tiling them in the horizontal, but you can tile them in the vertical as well. But if I just sort of step through here, what you can see is as you step through, that as you move from one area to another, you can still see that the Hamming distance is preserved as you move across. So we can tile things together. We're not limited to having, say, 10,000 pixels here. We can have another 10,000 here, or if you're just using 1,000 dimensional hypervector, you could have 1,000, and so on. So you can have as big a cognitive map as you like, and be able to represent the Hamming distance as a measure of how far you are from any 2 points in the plane. You can also do that with the circular hypervector, and I'm going to come on to talk about one of the cameras that we used a little bit later on. But we use one of these spiky neural network cameras for part of the work. But if you want to build a cognitive map to work out where you are, one of the things that you can do is when you build your cognitive map, rather than using this as the XY position, you can simply have some fixed points within your field of view from any point in this area, and at each point here you can just bind together or bundle together the angle at which you can see the various objects. So you know the object type potentially, you know the angle, and so using the circular hypervector at each point in your cognitive map, you can know where you are just by comparing what you can see at that point, the angle of the objects. And if I sort of step through that, you can see that it's predicting where it thinks it is based on just moving through the map and looking at the angle, the vector that represents the angle of the different objects that it can see at that point. Now, if you want to go a bit more complicated than that, you can have something like this, where you've got an agent that's trying to move through this maze, but all it's doing here is just using the angle. It knows angles to blue objects, for example, and it can still, it's a bit like an A-star algorithm, but using angle, it can navigate around the maze, and it can find the objects in a sequence. It's searching for things in this sequence, but you'll see that all it's doing is finding the path by just using the angle, or the angle that it has in its memory from each location that it finds itself at to where the object is. So that's going to be important a bit later on when we come to look at our agent performing some tasks. but it can either use circular hypervectors, or as we'll see later, we can use the linear hypervectors to measure the distance from any object to our current location. We then have to think about the decide loop, about memory and learning and reasoning and planning. And in military terms, what you're trying to do is plan a course of action. You have a sequence of things that you want to do, so you have to be able to represent these sequences. And of course, we can do that very easily with our VSA vectors, because we can either use cyclic shift to represent sequences, or we can use roll filler binding to represent that. And here I'm just going to show you what happens if you're trying to achieve a goal. Again, in the previous couple of slides, I showed you that you can do this with angle. In this particular case, we're just doing exactly the same thing, but we're just using the Hamming distance between the current location and the goal, and that's shown in the color there. So essentially, the agent's moving to the brightest area from its current location to navigate to the goal. It's essentially analogous to an A-star algorithm, if you're familiar with the planning literature. Now, what you might want to do is something a bit more than just go for a single goal. What you really want to be able to do is have an attention mechanism that lets you plan a course of action that might, for example, and this is just a simple example, suppose you want to make a cup of coffee or something, then there will be a sequence of things that you want to be able to do, and you can represent that sequence of things just by taking vectors that represent those things. So they can be random vectors, or they can be semantic vectors for a cup and a kettle and so on. And what you want to be able to do is place these objects in your grid and create a cognitive map that will allow you to navigate through whatever obstacles are there to be able to make a cup of coffee. And the other nice thing that you can do is, if you've got something like a cupboard, you can actually represent the cupboard by the things that are in it. So there could be the coffee, the tea bag, and you just do that by bundling vectors that represent these different things together to create your cupboard object, or a refrigerator object, could be milk and yogurt and so on. And so we did that, and essentially we create a vector that tells us how to make coffee. We call it a make coffee vector, and it's just simply the kettle followed by, you need to find a water, you need to find vectors or the position of things that represent a cup. And because the cognitive map has simply bound the location of these objects with a semantic vector that describes the object, and we used a large language model to get those semantic vectors, we can now step through and create a cup of coffee. So as we go through, you can see that the first thing we have to do is to find something that represents the kettle. So the kettle is the blue object. After it's got the kettle, it needs to find some water, so it's going for this little blue thing here. And then following that, it has to then find some cups, and it finds, in each case, it finds the nearest cup whilst avoiding the obstacles. It then needs to find the cupboard with the milk or the coffee, and you can see it's just navigating around, and it's finding all of these things. So we have the ability to plan and make decisions, again, all just using the vectors. And so what we like to be able to do is to end up with something a bit like the Boston Dynamics dog, doing all these clever things. But what we'd like to be able to do is to do everything using this common representation, and the common representation will be binary hypervectors, and our cognitive brain, if you like, is this common representation in a hypercube of everything, whether that be images from cameras, or whether it be the actuators in our robot or whatever. Everything's going to be done in vectors. And what we're trying to do is try to do everything using in-memory processing with a little bit of near-memory processing. So we're trying to do everything as in-memory processing, so that we can use some of the ideas that IBM have been developing in Zurich to use some of their vector processing chips that can do the binding and bundling very efficiently and very, very quickly. So to build a demonstration, we had to come up with something that was militarily relevant, but not too challenging, so that we could actually build things very quickly or simulate something very quickly to allow us to demonstrate how we would do this just using vectors. And so the basic idea that the customer came up with was, could we have some sort of robot dog that could visualize a soldier making gestures that told the dog what to do? For example, follow me, or go and find something, or I've got a problem, can you go and help me solve the problem? So we're going to do that with hand gestures. And so that's the observe phase. We then need to decide what it is that the hand gesture is telling us to do. We need to orientate to that hand gesture. We need to know something about the environment that we're in, and we need to be able to then plan a course of action. We need to decide what it is we need to do to obey the command that we've given with the hand signals, and then at the end of that, we've got to be able to perform the actions required, and then we keep going around and around the loop until we've achieved the goal. That's the basic idea. Now, we couldn't afford one of the Boston Dynamics dogs, so what we decided to do was to use some real cameras, but we decided we'd simulate the environment in which the robot is operating. So we're going to simulate that environment, but the cameras are actually going to look at the output from, we actually use the Unity simulator, the actual view that the agent in the simulation has, and from the observations from the camera, convert those into vectors and then drive the dog to actually perform the task that it's going to be asked to perform. So that's the basic idea. So here's the sort of description. We've got cameras. We use two types of camera. We use a frame camera, and we use a spiking neural network event camera. The event camera is going to be there to because it's good at recognizing changing things in the scene, and it can recognize gestures. And the frame camera is going to be there to recognize the objects and the position of objects. We want to generate vectors from those cameras, not only what objects are in the field of view, but what angle are we looking at a particular time. We want to do our OODA loop processing, and we want to be able to drive the simulator, the agent in the simulator, everything using vectors to be able to perform the task. And in the environment, we can also call out to other agents, and as you'll see, we can call out to agents in the cloud where we might get the support of a large language model. So that's the idea, but everything's got to be done in vectors. That's the main message. So what we've got in our simulation is we have this soldier, this human, who's going to perform gestures that we have to recognize. We've got various objects in the environment, rocks and things to avoid, trees to avoid, but objects of interest. And we can communicate, but we want to minimize the communication because we're at the edge of a network, and we don't want to have to use large amounts of bandwidth to be able to get information to and from other agents or to and from the cloud. And in the environment, we've got all these barriers that we have to avoid, as well as the rocks and so on. So that's the gist of the environment. So I'm just going to take you through very quickly the sorts of things that we had to do. So one of the things that we did with the University of Strathclyde was they have techniques for taking spiking neural network cameras and being able to train them to identify various types of gestures. So the gestures, as you'll see, are gestures that are being performed by the human agent in the simulation. But we actually trained the model that we're going to use on gestures made by a human in the lab, just to show that we weren't just using things in the simulation environment. So if I kick this thing off, the agent itself is the agent dog. It has to scan around. So you see it scanning from left to right until it detects a person. And if it detects a person, it looks at the camera that is observing the gestures of the person, and we do a hypervector generation from the spiking neural network pattern to produce, in this case, a 1 or 2K VSA vector. We start off with a 10K vector, we just truncate it to whatever size we want. And in the experiment, we found that we could do different types of gestures. We could do gestures that we were going to interpret to be follow me. We had two types of follow me gesture, as you'll see later on. We had a way of identifying that it was a person making the gesture, and we had gestures that told us to go ahead. We had gestures that said pointed a gesture, a pointing gesture that was going to be interpreted as I've got a problem. Can you solve the problem for me? So I'll explain how we do that as we go through. So the first thing is, how do we do object detection? The spiking camera is great for temporal things like gestures, but if we want to represent or recognize different objects in the environment, we used two other things. We used Dino as a way of detecting if there were objects in our field of view. So Dino just basically finds the objects and just puts a box around the object. And then for each object that was detected by Dino, we used a Google Vision Transformer to convert whatever was in the box into a vector representation, which was mapped into 10K and then down to 2K binary vectors. And we then trained it by just having an agent wander around the environment, looking for different objects that it could see in the environment from lots of different angles. And here you can sort of see the principal components of that. But we actually ended up with a 98.4% classification accuracy for all the objects of interest that we've got in our environment. So you'll see there's a shelf, there's some rocks, soldier, tree, crowbars, boxes, all sorts of different things. So the idea now is can we store just a few representational vectors to represent these different classes, and can we just have a minimum amount of storage inside our agent's memory? So what the agent has to do now is, so it has to scan first of all, and if it detects a human and it's been told to follow me, which it was in this particular case, it now has to try to keep the human in the center of its field of view. So it's doing this all with vector representations. It's taking the vector of what it sees. If the human's there, it then takes the next best action, which is try to move towards the human, and at the same time keep the human in the field of view. If the human disappears, the logic that we used was simply the human must have gone behind something. So if there's a barrier of some sort, like the gap here in the wall, aim for the gap in the barrier, because that's probably where the human's gone. And as you'll see in a moment, that seems to work reasonably well. So I'm going to just run the video through first very quickly. So the agent's seen the human has gestured to say, follow me. Now the agent has to try to follow the human, but as it's gone through the barrier, it doesn't know where the human is. You see it scan around looking for the human. If it can't see them, it goes through the barrier, then it looks for them again, it finds them, and it keeps following. And all this is done with this OODA cycle just using vectors. So it's an in-memory processing function where vectors trigger other vectors. We're not using any other logic. And you'll see that the agent has followed the human up to a particular point. And I'm just going to take a few moments to explain what it was doing while it was doing that, and then I'll show you how we solve the next challenge. So in order to perform these tasks, we have to store various things within our memory, within our hypercube memory or hypervector memory, and we actually only have to store quite a few things. We have some role vectors, so every object has a description. Every object has a camera vector, as a role. So it has a description vector as a role, a camera vector as a role, and what we call a workflow vector as a role. And we then have different component vectors. So each object, for example, a human, will have a description vector. There'll be, and by a description vector here, you'll see one says, this is generated using a large language model embedding of the object type. So this is a semantic vector that describes a human. So we actually just use a description of a human to use a large language model to create a semantic vector, and then we map that into a 10 kilobit vector that represents the human. And we do that for all the different objects in our scenario. So we're not dependent on having an exact naming for a human or a bot, a crate or whatever. We're using a semantic description and using a large language model to give us these sort of fuzzy descriptions of the objects in our scenario. So we've got object components, there's the description. The camera vector is one of the exemplar vectors from our training of what the camera can see. And then a workflow vector, each object has a workflow of things that you can do with that object. How do you interact with it? And in order to create a workflow vector, all you do is you just bundle together role filler pairs that give you a sequence of things that you can do when you interact with that object. You need to read the paper to get all the details of this, but we also have what we call object description vectors. These are the vectors for the different objects that are seen, and we have workflow description vectors that we're going to store in memory for things that we're trying to achieve. And then we've got different cognitive maps that we build as the agent's moving around the environment. And I'll just show you what those look like in the next slide. So essentially what we've done is everything's got this common representation in our hypercube memory. And what we're trying to do here now is as the agent moves through the environment, it's trying to follow the human, but as it's scanning around looking for the human, it serendipitously might see other things. So it might see the position of the rocks or the explosive crate or crate of explosives. It might see a crowbar, other things in the environment. And what happens is as the agent moves through the environment, it knows where it is. So it has a position vector that gives it its XY coordinates. But if it can see something at that point, so if it can see from that point a crate of explosives, it stores the angle at which it can see those explosives and just a record that it could see those explosives at that location. And then it sort of moves on. And what happens is as it's moving through its environment, here when it's at this location, you can see this is its field of view. It can see various objects in that field of view. And as it moves around, it builds up a cognitive map of the things that it's seen. So early on when we're here, the only thing that we've seen when we were at this location here, we were able to see from here, we were able to see the explosives crate. And so we've got a cognitive map that says at these locations, I saw an explosives crate. I didn't see it here because I was just following the person, and I didn't scan around all the time to be able to find all the objects. But as I move through the environment, I build up these cognitive maps. That's the basic idea. So as this agent has been moving through the environment, we left it looking at the agent. Now the agent's pointing, and the agent here knows that the pointing gesture means there's a problem. I've got something that I'm pointing at, and the agent looks at what it's pointing at and it recognizes this as a pile of rocks. And the question is, how do I get rid of a pile of rocks? Is there anything that I can do to get rid of this pile of rocks? So this is all that we sort of made up to tell the story. But essentially, the agent doesn't know how to solve that problem. So the question is, how can I solve the problem? Well, as I've been wandering around the environment, I've seen various things. I've seen this rock pile. I've seen the human who's told me there's a problem with it. But as I was wandering around following the human, I saw this object here, which it turns out to be a detonator. I saw crates and a crate with this thing called explosives, so they're slightly different crates. I saw rocks. I saw another crate here, and actually in here you'll see it's very difficult to see it in there, but it actually saw a crowbar. And so it's built up some knowledge of things that it's seen. And so the idea that we had was, well, could I call out in some way to a large language model to be able to find out what plan I could use in order to solve this dilemma of how do I remove a pile of rocks given the objects that I've seen. So it's all a little bit contrived at this point, but essentially what we do, because all the objects have been described semantically, we can create a vector embedding, which is a query that basically says, I've got an objective, which is to clear a rock pile, and I've got these known objects that I've seen, and we can represent all of these as vectors, create a bundled vector which has the objective and the known objects. We can pass that to a large language model, and the large language model then has a prompt that it just fills out with the things that are in this vector representation. So it says, give me a plan to complete objective X. I've seen the following useful potential objects. And the LLM comes back and says, well, I can give you a digraph that tells you some plans, and we can represent those plans again as a bundle vector. And so we've got a bundle vector that gives us options as to ways in which we might be able to remove the objects. One is grab some explosives, find an explosive crate, because that's what you've seen, grab some detonator plunger, use the detonator plunger, and that might solve the problem. That was the idea. But the point here is that communication that we made was only one vector. So it was only, it turns out we used 2 kilobit vectors for the whole of this. So it was just a 2 kilobit transmission to send the information to the large language model, and a 2 kilobit vector to be sent back. So a very low bandwidth requirement. So we receive that new plan in our cognitive memory, and what we now do is we say, okay, I now need to go and find these things. So I need to go and find an explosives crate, or a detonator plunger, or a crowbar, or whatever it is in this plan. And so what the agent does is, just by querying, and a query here is just doing an XOR with a bundle vector, you just say, I want to find where is the nearest object that I've seen. And I look at my cognitive memories, and in my cognitive memories, this is where I am. The nearest thing, the last place that I saw something that was in my plan was here. So I need to be able to orientate, at least if I get to there, I know I'll be able to see it. But so can I get there? And if on the way, if I see it before I get there, can I find a shorter path to the object? That's basically what it's trying to do. So you'll see that working out here. It now tries to navigate using the timing distance to find the next best move. As it goes through the gap, or where the detonator was, so it navigated to the detonator. Once it's found the detonator, it's going to change the cognitive map to the next nearest thing, which was the crate. But before it's even got down to where it saw the crate, it did a scan and it found the crate. It now scans around again, trying to look for the crowbar, sees the crowbar, and now it goes to the crowbar. And as it goes along, it's adding to its cognitive map the path that it took where it could see the crowbar. And now it needs to go back to the pile of rocks. And so it's navigating back, again, scanning the environment as it goes, building up its cognitive map. So if it has to do other things, it's got a much more rich cognitive map to deal with. And when it gets back to the user, it couldn't bring these things to the user because it didn't have those capabilities. But at least what it can do is tell the human, this is where the things are, just by probing its cognitive map, and these are the safe routes that you can take to find all the objects that you might need to solve your problem. So that was the general idea. And of course, it can pass the instructions that it's got in its memory, the plan, to the human as well. So that was the sort of basic idea of the plan. And then the other thing that we didn't really touch on was, well, what happens if I see a gesture that I'd never seen before? So in this particular case, when it sees the agent now makes a completely different gesture, a salute. And the agent doesn't know what that salute means. And so what it can do is it can just take the vector representation of that and make a broadcast query, again, just a single 2 kilobit vector that says, this is an unknown gesture. Does anybody know what this is? So if there's an agent out there that receives that and knows what it is, that agent can just send back a vector representation of what it is. And that tells me what the object is. It gives me the name of the object. It gives me the known exemplar vector for that object. And then I know that what this gesture means is it's another way to say, follow me, for example, in this case. Now, I'm not going to go through all the details. You have to read the paper for this, but essentially what we're doing is this big flow chart, but what we're trying to do is to do everything we're just using vectors to do everything. And what I mean by that is just a section of that process. But when the camera is looking in a particular direction, the objects that it sees become vectors. They're bundled together as a bundled camera vector at that angle. What we do, that's the vector that the agent has seen, but it's a noisy vector. And what we really want is to say, I want a clean vector that better represents these objects. So I pass this vector into a cleanup memory. Vectors that are within a Hamming distance threshold fire, and in our model, they trigger clean versions of these vectors. So these are the clean versions of the vectors, and all we do is bundle them together. So what we end up with is a clean version of what the agent saw, and we can then, on the basis of that, we can store that in our memory. That's the basic idea, and we can then trigger to the next unbinding angle, and the scan moves on to the next angle. If it sees a human, then what we want to do is trigger the next best move. So when this vector comes in, if it triggers the human vector, I've seen a human, what we do is we know that's now in the angle that the human is at is the current look angle. So we want to reset our scan angle to be the current angle, and then we want to scan either side of that, which is this scanning the new angle to find where the agent has or where the human has moved. So that's the basic idea behind the whole thing. So just in conclusion, what we were trying to do was to show to our customer that we could do these cognitive operations just using vectors, and we actually showed that we could do all of this using 2 kilobit binary hypervectors. What that meant was we could do all of this processing in just 500 kilobits, and the only transmissions that we had to make to the agent in the cloud, the LLM, or to another agent was just a total of 8 kilobits. So from a military point of view, that's really important because you're not using any bandwidth. You just don't have any bandwidth on the edge of the network. But you could still call out to use these other agents or other facilities. So we demonstrate we could interoperate between a brain-inspired sensing and VSA processing, efficient and effective VSA planning. We can exploit large language models if we want and represent everything in the same vector representation. And we can do local one-shot learning using knowledge exchange at the edge of the network. And so the message that we tried to convey to the customer was all you need is large orthogonal vectors, or all you need is love. And we need to write a paper on that, I think, with that title. I'm going to skip all the conclusions because you can see that at the end, and we're running out of time. But this was for DSTL, the UK customer. And the question is, did we get the message across? Well, they were quite impressed by what we were able to do just using vectors. And so they made their own video to pass the message on to others. So I'm just going to just skip through those conclusions and let you see their video.
AI and machine learning are rapidly advancing the UK defence's abilities to understand situations and take actions faster than our opponents. But current AI needs massive computational and data resources tied to data centers with reliable cloud connectivity, making AI hard to exist where it's most needed, at the edge of the network, for dynamic and contested multi-domain operations, and the realities of limited connectivity and computer resources. To meet this challenge, new paradigms are needed. To think differently about AI. To be more like the way humans think. A huge step in innovation. VSA is an algorithm and data technology inspired by the human brain's adaptivity. Sensors that perceive the world the way human senses do. Data formats and processing which mimic the complex network of spiking neurons and distributed cognition. Algorithms that achieve situational understanding inspired by human memory, reasoning, and planning, enabling new observations to be integrated with existing understanding, to learn and reason, plan and communicate in VSA. Embodying a new level of applied intelligence. And because this technology also needs fewer resources, power, weight, size and communications bandwidth, it's enabling a new level of AI deployment at the edge. Across all domains, devices using a resource-efficient approach. The future of defense. Rapid and resilient information advantage, right at the point of need.
And I'll finish there.
All right. So, Graham, thank you very much for your presentation and the great video at the end.
Yeah.
Fantastic. So, let's see. Let's open the floor for discussion. So, anybody? I have a couple of questions on my own. Maybe I can start just to increase my or improve my understanding. When you speak about LLMs and vectors, do you mean that you want to modify LLMs to work with vector representations as tokens somehow, or integrate VSA into LLM, or?
No. So if you take a typical LLM like BERT, okay, as an encoder, right? If you look at the internal representation, you'll see that there's a CLS token in the representation of the vectors at different levels in the attention heads and so on. The CLS token basically is a vector that describes the thing that you're trying to encode at that level. So it might be a 300 or a 600 element real valued vector. But what you can do is you can just do a random permutation to map that onto a 10 kilobit hypervector. And that's all we do. So you can do that with any LLM. And what you're getting then is a semantic representation. So when we describe the objects in our scenario, what we did was to use BERT as the model. We would describe a crate as a box or a crate or whatever it is. So we get something that semantically represented the crate rather than just spelling the word crate. You have a semantic vector that you get from the LLM, and that then becomes a 10 kilobit vector or a 2 kilobit vector in our case. And so you've got a common representation of everything.
Hmm.
That's the idea. So your images, your gestures, everything just becomes a vector. And so you can map from LLMs to vectors, you can map from deep neural networks to vectors because they're all, internally, they're all vectors. It's just that we want the vectors to be in a particular form. So
Hmm.
we can use the hypervector properties to be able to bundle things and bind things together. So that was really what we were trying to get across. We have a common representation of everything, and then all the processing is done just using vectors. And the big advantage of that is that if we were to use things like the Hermes chip that our colleagues in Zurich, IBM, have developed, we can do the binding and the bundling operations in a single clock cycle, for example. So you can do things very, very quickly using that type of technology. That's the thing that excites them, that they can do things faster and they can have a common representation for everything. So you've just got to learn a different way of doing programming. You've got to learn how to do in-memory processing.
Hmm. Okay, thank you. So let's see if we have more questions. Penty.
Okay, I'd like to comment on the difficulty of making people to understand what we're doing. And I just compared it to the problem of explaining that a number like 5 into power 0 is 1.
Yeah,
And because it's counterintuitive that something that's there only 0 times, that how can it be 1? Like 5 put to x power 0 or 10 to power 0, they all 1.
yeah,
And then by the time we are in college, we don't even think about it. We just use it. So I think something like that needs to happen here too, that people they struggle it for a while and all of a sudden it just sounds natural.
yeah.
And so just looking forward to that time. It'll come.
Yeah, I mean that was one of the reasons we did the silly idea of the smoothies.
Mm,
You're talking to soldiers, and trying to get across. They don't even know what a vector is half the time.
mm,
But they got the idea straight away of, oh, it's a
yeah.
common representation. I can map it back into the original thing, and they
Mm,
got the idea of a distributed representation because they could see that their fruit was distributed through the
yeah.
smoothie, but you could still
Hmm.
recover it. So once you've got that idea across, then they've got the idea that you have a vector of
Yeah.
vectors,
Yeah.
and and that's the key thing. And then you
Yeah.
try to explain to them, but this can be a semantic representation. So you
Yeah.
it's not just the words, but it's the
Yeah.
meaning. And that's the thing that we've been trying to get across all the time. So with the gestures, for example,
Mm,
that was really interesting that we could actually train on real humans making the gestures. But when we
yeah.
applied that training algorithm to our simulation environment, it worked. It still recognized the same
Yeah.
gestures.
Yeah. Very nice. Thank you.
Yeah.
All right, more questions? We have room for maybe one, two more. Tim?
Yes. Oh, microphone. First of all, thank you for the great presentation. I was curious, you showcased that there's this massive bandwidth and compute performance advantage over comparable traditional methods.
Yeah.
And I was wondering, since you've got that advantage and such low sort of power requirements, have you considered also putting at least part of the decision-making logic onto the forward agent, the agent A?
Yeah.
Because now it is dependent on the LLM on the network, right, for actually making any decisions.
Well, so the idea was that there'll be certain things that the agent already knows. So, I mean, once it's got that plan from the LLM, it knows that that is a plan for removing rocks. So it's in its memory. So you can pre-program the agent with behaviors to solve particular problems based on the gestures that it's receiving from the human. So what we wanted to do was start off with very little knowledge at all, and then let the agent learn. But once it's learned something, it's then in the memory, so it's got a workflow. The other thing that we had was this thing of, for example, if you've got a crowbar, the crowbar itself is described by a name, which it gets from a large language model, a semantic description of the crowbar. It's got a vector that describes what it looks like from the camera, and it's got a workflow. In other words, what can the agent do with this object? So now you can start to do other types of reasoning. For example, we were thinking of the idea that it could work out for itself that if it needed to get into a crate, it could use the crowbar. It's that sort of logic. But all our workflows are just simple linear workflows in this particular case. And we've done a lot of work in the past on more complex workflows with branching and all sorts of things. And in fact, a parallel project to this one, a company in London took the VSA idea from previous work that we'd done and demonstrated that they could perform all sorts of very complex workflows at the network edge, with a very low bandwidth communication between the different elements that were performing those tasks. So they would have distributed sensors, and they were trying to monitor a road, and they would see vehicles going down the road. They would then have to call in a drone and all sorts of other things. So the sort of things you're seeing going on in Ukraine, it was doing that sort of thing, but it was just using vectors to do it. So you're right that you can let the agent just do what it's capable of doing, but we have the ability to, when it doesn't know what to do, to actually ask for help. That was the idea.
Very impressive. Thanks.
So let's see if we have a last question from the audience. Penty?
No,
Or
I
a
just
comment?
I
Or a
was just
comment?
I was just chiming on that the agent do what's capable of doing. I would say let the math do what it is capable of doing.
Yeah. Yeah, of course. Yeah.
All right, then. So thank you for a great discussion, and thank you, Graham, for the excellent talk.
Okay.
So I think it was a fantastic opening of the season. So stay tuned and have a nice day wherever you are. So see you in 2 weeks from now. Bye, everybody.
Bye.
Thank you.